Welcome to the second session about type functional programming in Haskell. In this session, we'll cover the following learning goals. What are the learning goals of this session? Well, after the session, you should be able to understand common Haskell functions on lists and their types. You should understand lazy evaluation and its semantics as it appears in Haskell. We've already seen something very similar for Scheme, but now it's Haskell time. And you should be able to write programs in Haskell that make use of lazy evaluation. You should understand the list functionals, map, fold left and fold right, as they appear in a typed setting. You should be able to understand and use ranges and list comprehension as they appear in Haskell. You should be able to use user-defined recursive data types to define structured data. And you should be able to define recursive functions over data types. Let's start with functions on lists. We've already seen lists in Scheme, and we've already had a taste of how you can work with lists in Haskell. And the same functionals that can be used in Scheme can of course be defined in Haskell. The best known one may be map, and the behavior of map is that if we apply map to a function f and a list x1 to xn, then this should return a list of f x1 up to f of xn. And this functional map is predefined. It's found in the standard prelude of Haskell, so you don't need to write down map yourself. But let's try to define map ourselves as map prime, such that we can find out how it's implemented, and also let's find the type of this map prime, which really is the same as map, has the same behavior as map. So we're now going to define a function map prime. The reason why we call it map prime is that the map function is already part of the standard prelude of Haskell. Map prime is a function that will take a function f and a list and return the list consisting of the elements of the original list with f applied to each of them. And we define map prime by means of pattern matching with respect to the list. So the first clause of the definition of map prime will be a clause that tells us what to do with the empty list. And here nothing happens because f applied to all the elements of the empty list is just the list, well, same list, the empty list. So the other more interesting clause is that of map prime and f and a non-empty list, a list with head x and a tail of x's. And what do we get here? Well, we get a list, and the head of the list is f applied to x. And what's the tail of the list? The tail of the list is what we get by calling map prime recursively with f and xs. So that's map prime for you. Let's save this and send it to the buffer. What do we get? We get this. Yes. Let's try to apply map prime to a function. Let's use the anonymous function lambda x plus 7 and apply that to the list 1, 2, 3, 4. What do we get? 8, 9, 10, 11, just as expected. Now you might wonder, what is the type of map prime? Map prime is a polymorphic function, and let's see what the polymorphic type of map prime is. Well, now what is the type of map prime? Let's find out. Map prime is a higher order function. It takes a function f as its first argument, and after that it takes a list as its second argument. So since map prime takes a function f as its first argument, its type must be t to t1 for some types t and t1, and after that
its second argument is a list, and since f is applied to the elements of the list, and we can see that f is of type t to t1, we see that the second argument must be a t list. And we see that the resulting list is a list of elements of type t1, so the result type of this function is a t1 list. Let's see what Haskell says about this.
System about the type of map prime. And indeed, the type of map prime is t to t1 to t list to t1 list. And we notice that we haven't specified what t and t1 are. So map prime is a polymorphic type. Map prime will have type t to t1 to t list to t1 list for any types t and t1. Map prime is a polymorphic function.
The filter function is actually a specialized fold of fold right, which we will encounter later. The filter function takes a list and a predicate and leaves us with the elements that satisfy the predicate. For instance, if we have the predicate huge of x, which is true if x is greater than 2, and we have the list mylist 5, 4, 1, 2, 6, 7, 1, 2, we'd expect that if we filter mylist with respect to huge, filter huge mylist, we would get the list of numbers in mylist that are greater than 2, which would be 5, 4, 6, and 7.
Filter is a function that takes a predicate and a list as arguments and returns the sublist of elements for which the predicate is true. Now, filter is also part of the standard Haskell prelude, so we'll call our version of filter filter prime. So filter prime takes a predicate p and a list, and again we use pattern matching to define our function. First, we define how filter prime acts on the empty list. We get back the empty list. Next, we'll define how filter prime acts when applied to a predicate p and a non-empty list with head x and tail xs. Well, if p of x is true, remember predicate is just a function that returns a truth value. If p of x, then x belongs in the result, so x is const onto the result of applying filter prime with the predicate p and the tail xs. Else, if x does not make p true, then x does not belong in the list, so we simply call filter prime of p and xs. So now let's define the predicate huge x, as we saw before, the one that's true if x is greater than 2, and have my list be 5, 4, 6, 9, 1, 2, 10. And let's send this to Haskell and see what happens if we call filter prime on huge in my list. Yes, indeed, we have the sublist corresponding to all the elements in the original list that are greater than 2. So yes, that's indeed the case. Now the burning question is, what is the type of filter prime?
Now, to see what the type of filter prime is, again remember filter prime is a higher order function. Its first argument p is a predicate. A predicate is a function that takes an element and returns a truth value. So p should have type t to bool. And as our next element, we take a list, and this should be a t list, of course, because we're applying the predicate to the to our T list. So this and that should be the same type. And we're returning a sublist, so the result type of this function should also be a list of type T-list. So that's what we claim filter prime has as type. So let's see what Haskell has to say about this.
Haskell says, let's find the type of filter prime. And indeed, it is the case that filter prime has type T tuple to T-list to T-list. And again, when we figured this out, we made no assumptions about T. So filter prime has this type for any type T, so filter prime is also a polymorphic function.